Hey there guys and girls, back at you with another video on magnetism. In this situation, we are seeing what happens when you try to reverse what we learned so far about magnetism. We're going to call this adventure electromagnetic induction. So here's the idea. We've learned so far that a current can create a magnetic field. Today we want to know if the reverse is true. Can you create a current from a magnetic field? And so the person that tested this idea was a fellow by the name of Michael Faraday, who in the year 1831 or so actually passed a magnet through a coil of wire to see if he could create an electric current from it. And so a basic picture might look something like this. You got a coil of wire hooked to an ammeter, and then you put a magnet inside of it. A picture of his experiment would look something like this. This is a sketch from his notebook. And there's your magnet, because it's a coil of wire connected to a battery. And then here's the coil, and then he's got it connected to an ammeter. And so some observations from this experiment. He observed that when the magnet was at rest inside the coil, so he just placed it inside the coil, that nothing happened. But he noticed that when the magnet was moving, keyword moving, in and out of the coil, then there was actually a current created. So again, keyword here is that the magnet had to be moving in order for this to happen. He also noted that when the direction that the magnet was moving was reversed, that the direction of the current was reversed as well. And so to kind of summarize that in a picture form, when we had the magnet at rest, nothing happened. When the magnet was moving, then we saw a current created. And then when we moved the magnet in the opposite direction, the current went in the opposite direction. And so physically what you would notice on the ammeter as you're doing it is that in one situation the needle would move one way, in the opposite situation the needle would move the opposite way. So to kind of carry on with these observations, the last thing that he noticed was that the faster the magnet was moving, the greater the current got. And so that and the other observations should make a little bit of sense to you. Like it should not be surprising that the magnet being at rest at nothing, if you think about it in terms of energy. Remember, energy is a big arcing concept. We can use it to explain whatever is applicable. So in this situation, when the magnet is still, the magnet has no energy, and therefore it has no way to do any work on those charges. And so it can't create a current because it can't make the charges move. When the magnet's moving slowly, it's got a little bit of energy, meaning it can do a little bit of work on the charges. And so we would observe a small current. And it's not until the magnet is moving rapidly, so at a high speed, that it has a lot of energy, and therefore is capable of generating a big current. And so if you think about this in terms of energy, then those observations should make sense. So let's see if we can figure out how to find how big that current would be. And this is typically known as Faraday's law. It's Mr. Faraday who came up with it. The word induced basically means to cause indirectly. And so we call the current that's created by the moving magnet an induced current. And so that's what the word induced means. Just like all currents, an induced current has to be caused by an EMF, or a voltage. And we say that the magnetic field creates an induced EMF. So to kind of give you an idea of the differences, here's our old kind of circuit where we had a battery. And the battery was a source of EMF. We can kind of think of that as a localized EMF. Like there's one thing in the circuit, this thing, the battery, that can create the EMF that causes the charges to move. In the situation where we induce a current with a magnetic field, so it's changing magnetic field, we might refer to that as a non-localized EMF, meaning that it exists all around the entire loop. And so again, it creates a current, and we call this an induced EMF. So in our old picture where we made currents with batteries, we said this is the thing that's causing the EMF, and you can point to and identify exactly where it is. For our new circuits where we create a current with a magnetic field, the EMF basically exists all throughout the loop. So everywhere in the wire we can say there is an EMF. And so that's why I say non-localized EMF, because it exists everywhere in the loop. Now we can still use Ohm's law to figure out how big the current is. So when I say figure out how big the induced current is, well, the new thing that we're figuring out is how big is the induced EMF. That's what we're really learning here. Okay, so Faraday came up with a relatively easy and simple way to think about the magnet and the coil. And he coined this term, or this idea, the term flux. The basic idea behind flux is it's the amount of something that passes through an area. Keyword being area. And so magnetic flux would be the magnetic field, that would be the something, that passes through some given area. So the amount of field B that passes through a given area A, and here for our area, that would be the area of our coil, would give us the magnetic flux. You can have sunlight flux, depending on how much sunlight goes through a window. That would be another example of flux and how it can be useful. The symbol that we give flux kind of looks like that, and that Greek letter is the Greek letter phi. It's kind of like a zero with a skinny eye through it. And then we use the subscript B to designate that it's a magnetic flux. And so to find the flux, we just multiply field times the area. The unit would simply be Tesla times meter squared, which, if this is ever a question on Jeopardy, is called a Weber. Because the flux is really kind of an intermediate thing, we really never use the term Weber. We just write Tesla times meter squared. So, last thing, in order for there to actually be a magnetic flux, the field and the area have to be normal to each other. Remember, normal is a fancy word meaning perpendicular to a surface. And so I'm going to put a little perpendicular sign underneath the B to make sure we remember that they have to be perpendicular to each other. Let's draw some examples. Here's a loop of wire. Here's a magnetic field going into the page. Into the page is normal to that loop, it's normal to the plane of the page, and so it would produce a flux. So if you imagine those X's as representing physical arrows, they would actually go through the loop, like in and out of the screen. If we take the magnetic field and we turn it to the right, now the magnetic field is not normal to the area. It does not pass through the loop, rather it passes parallel to the loop. And so in that situation, we would not have any flux. So let me give you kind of another intuitive example. Please don't write this down, just kind of follow along with me. Imagine for a second that you're a soldier at the Battle of Thermopylae. If you remember the movie 300, the guys that were fighting all the Persians said, we have so many people that our arrows will blot out the sun. So here comes a whole bunch of arrows towards you. And you have a shield. The question is, how are you going to use it? Draw some pictures here. You would probably want to hold it so that the greatest area of the shield face the arrows as they're coming towards you. So, here are arrows coming towards somebody. Here's them holding their shield like it's in the plane of the page, and that's bad because there's no area to intersect those arrows. So that guy's getting hit by a bunch of arrows. What would be better is if you turned your shield so that the big broad area of it faced the arrows. That's good. And so if you did that, then the arrows would stick in the shield and you would live to see the next barrage of arrows. In the first example, the arrow flux was 0. The field of arrows, if you will, times the area of the shield was 0 because they're parallel to each other. In the second example, the flux arrow is big. That's why the arrows were stopped by the shield. And so that's why that guy's holding his shield like that, so he doesn't get hit by those arrows. You can make a similar analogy using drops of water in an umbrella, but it's not nearly as interesting. But probably more practical for you and me. Okay, so back to stuff you'd want to jot down. So Faraday's law basically says that a changing magnetic flux, so when the flux is changing, you will get an induced EMF in a coil of wire. Furthermore, he states that the EMF induced is equal to how quickly the flux is changing with respect to time. And so we can say that the induced EMF equals the change in flux over the change in time. And just so we have everything together here, I'm going to rewrite the flux equation, and I'm going to rewrite Ohm's law real quick. And that way all of our equations are here in one area for easy reference. A couple things to note. First of all, like all of our other electromagnetism equations, this equation only tells us the magnitude of the EMF. So oftentimes it's written with absolute value signs because we're just looking for how big the EMF is. The other thing to note is that this is for one loop of wire. If we have n number of loops, well, we just take that bad boy and we multiply it by n. Not rocket science there. So let's look at a quick example. Let's say we take a coil of wire and we form it up into a square, and that the sides of that square are 10 centimeters, and it's pretty good wire, so let's say it's got a resistance of 0.2 ohms. So there's my loop of wire. And then we put it in a 2 Tesla magnetic field which is directed into the page, somehow, some way. So here's our magnetic field. But then over time we reduce it to half a Tesla. And let's just say that that time is 0.1 seconds. So it happens pretty quickly. And so here's our after picture. We've got a weaker magnetic field. And the question is, what is the induced current in this loop? And so you can kind of think of the flux as being equal to the number of arrows that show up in the loop. On the left-hand picture, we've got 4 arrows. The right-hand picture, we've got 1 arrow. And so the number of arrows through the loop is gone down, which means the flux has gone down. And so first thing we might do to solve this problem is figure out the area of the loop, so just side squared. And then we might use Faraday's law. And so the change in flux is caused by a constant area, so the area is constant, but a changing magnetic field. And so that's why I kind of wrote it like this, A delta B. That just kind of makes things simpler. Area is not changing, it's the field that's changing. And so my time was 1 second. The area doesn't change, so I'm just going to write that as 0.01 meters squared. And then we go from a final field value of 0.5 to, or from an initial value of 2. So final minus initial will look like that, which would give me 0.15 volts. And you may be going, where's the negative sign? All this really tells me is the magnitude, so I'm not going to write the negative sign. So to find the current, I just do Ohm's law, way back in the day. And so I divide my voltage by the resistance, and that would give me 0.75 amperes. So the last thing we need to figure out is what direction that current would go. And for that, we need our second law for today. We find the direction of the current using a concept known as Lenz's law. Lenz's law states that the direction of the induced current is such that it creates a magnetic field which opposes the change in flux. That's kind of a mouthful when you write it like that. So the direction of the induced current is such that it produces a magnetic field. So remember that currents create magnetic fields which oppose the change in flux. Kind of a simpler, more colloquial way to say that is to say the induced current tries to undo the change. So to kind of draw out a simple example, here's a loop of wire with a small magnetic field directed into the page, and then over time we increase the magnetic field, so we've got more arrows going through the loop. So what has happened is that our flux has increased, and it's increased into the page. So it's important to realize that not only is increased, but it's also increased into the page. In other words, we've got more X's inside the loop. So what's going to happen is that the current creates its own magnetic field, just like we learned at the very beginning of this unit, which will oppose the change in flux. And so to oppose more X's in the loop, we need dots to balance them out. And so that's why the induced magnetic field is going to be out of the page. So I'm going to put some blue dots in there just to kind of placehold the idea that the induced magnetic field, the induced current will create a magnetic field that is directed out of the page. And then the next thing to do is to use your right-hand rule, the very first one we used, to figure out what direction the current has to go in order to produce that kind of magnetic field. So what I would do is just focus on one side of the loop. For me, it's usually the right side that's easiest to think about. And then decide you need to point your thumb upward for your fingers to curl out of the page inside the loop, or downward for your fingers to curl inside of the page inside the loop. And so if you point your thumb down, your fingers would curl into the page. If you point your thumb up, your fingers will curl out of the page, which tells me that the current on that spot is upwards. So for the entire loop, because it would obviously kind of just keep going like this, the current would be counterclockwise. And so if we say what's the direction of the current, you would either say clockwise or counterclockwise. Or if I say what's the direction of the current on the right side of the loop, well then you would say upwards. Be as specific as possible, but also as general as you need to be. So let's look back to our example that we were working on just a second ago, where we have a magnetic flux directed into the page, but this time it's decreasing. We go from a lot of X's inside the loop to just a few X's inside the loop. So in order to counteract that page, the induced current is going to create a magnetic field going into the page to oppose the change. So it's going to try to keep the number of X's the same, basically. And so the induced magnetic field's into the page. Now use your right-hand rule, and again, I recommend use the right side of the loop. So just think about just this side over here to figure out what direction the current is. And so if you point your thumb downward over there, your fingers will curl into the page. So that tells you that the the current on the right side of the loop is going down. So for the entire loop as a whole, we would say that the current is clockwise. It would go like this. So the correct way to write my answer to our example is 0.75 amps clockwise. So that's the basic information stuff for today. Once we understand all this stuff, we can understand things like generators, transformers, microphones, those little credit card scanners at the grocery store, and then most importantly, why Nikola Tesla rules and Thomas Edison drools. These are all cool and super duper awesome things, but we will save them for next time. So until then, ta-ta.